Hi, I'm Alex Forsyth, and for most of my adult life, I've written code for a living. I've worked on animation production pipelines, home video games, theme park rides, and VR attractions. I've written optical tracking systems, control systems for location-based games, tools to make artists' lives easier, tools to automate complex build processes, and good old-fashioned gameplay code. And I've produced tutorial videos about scripting and 3D animation applications, and of course about Unreal Engine. I've been fortunate to work on some really cool stuff in the entertainment business, but a few years ago I started working on a SaaS product at a startup, and in the process I learned a lot about building applications for the web. More recently, I've been using that same skill set to build my own product, Bigtime Stream Tools. In this video, I want to explain how Bigtime works, but I don't want to assume any prior knowledge of web development. Instead, we'll build up our understanding as we go. We'll tackle some basic concepts, then we'll look at the design of some backend services, and we'll consider how the user-facing front-end app affects the design of our platform. After that, we'll take a deep dive into the design of Bigtime scripting system. We'll see how it is that a user can log in, connect their Twitch account, and write a script like this simple example, which changes their stream title whenever they get a new follower. And then we'll see how we respond to external events by executing those user-supplied scripts. Finally, we'll conclude by reviewing the design of the entire platform. So let's get going. Let's say you open your browser and type in the URL for our website, bigtime.stream. It's fun, you should try it. Your browser takes the domain name bigtime.stream and resolves it to an IP address. This gives it the address of a web server where the site is hosted. So the browser opens a connection to that server and sends it a request. Web servers use a protocol called HTTP. This message is just your browser saying to the web server, hey, please give me whatever you've got for the homepage of bigtime.stream. The server responds with an HTML document, and that document can instruct the browser to load more files. There's CSS to style the page visually, and then there's JavaScript to make the page interactive. Once all these files are loaded, we've got our app running in your browser. This is the web app, or the front end. It's the thing that you interact with as a user, and it's running on your computer safely confined within your browser. In this context, it's the client sitting opposite any backend servers it might want to talk to. Both the front end and the backend are running code that we've written. The front end app runs in your browser, and it's restricted to only doing things that the browser lets it do. Our front end is written in TypeScript using a framework called Svelte. Backend applications run on servers that we control, so they can do basically anything we want them to do. Our backend is written in Go and deployed to cloud-hosted servers. We're responsible for configuring the infrastructure for our backend, and we use Terraform for that. One of the things that front-end code can do is send requests to the backend. Our backend servers use HTTP as well, so for example, we can send a message that says, hey, I'd like to log in with this email and password. Is that okay? Then we can write our own backend code to handle that request. An HTTP server is a pretty simple thing. It's just a program that reads in HTTP requests, does whatever you want it to do, and then spits out a response. Handling login requests is just one thing that our backend needs to deal with. Once we log in, there are a host of other unrelated features that our backend needs to facilitate. For example, I can connect my Twitch account to the platform, which causes the app to send requests to the Twitch access server in our backend. I can create custom collections to keep track of videotapes or games or whatever things I want to use during streams. Those requests go through a collection server. I can define custom data that I want to keep track of for the different kinds of streams I might do. Those requests go through a broadcast server. And one of the key features of Bigtime is that it lets you write scripts to define custom logic to be run in response to different events that occur on Twitch or elsewhere. So there's another HTTP server that lets the front end interface with the scripting system. As we've seen, there are many different problem domains that our app has to deal with: Twitch accounts, collections, broadcast data, and so on. We can think of our backend as a bunch of different services, each one handling its own unique chunk of our platform's functionality. As we dive deeper into Bigtime's backend, we'll see how these services are put together. We'll look at authorization to see how these server-side applications protect your data, and we'll see how we handle securely connecting your Twitch account. And we'll see how some fairly simple building blocks come together to create a cohesive piece of software that can do some pretty complex and interesting things. So let's work our way into the backend. For an app like Bigtime, where users log in and manage their own private data, one of the first things we need to think about is auth. In fact, there are two separate concerns here. Authentication and Authorization. Authentication is about determining the user's identity, verifying that they are who they say they are. This is particularly relevant to the front-end app. We're interacting directly with the user, so we want to know things like their name and email address. As far as the backend services are concerned, though, we mostly don't care about who the user is. We just want to ensure that we're only exposing the data that they should be allowed to access. That's what authorization is about. Our application is multi-tenant, which means that we keep track of data from multiple different organizations. All of your data, regardless of what service is handling it, belongs within your organization. Organizations are a separate concept from users. You, as a user, own the organization that contains your data. But you can also invite other users to your organization with different roles that restrict what they can access. So in this example, authentication answers the question, is this user really Alice? While authorization answers the question, what operations is Alice permitted to perform in this organization? These are the design constraints that we have to keep in mind when we think about our app's security. So let's look under the hood and see how we handle authorization within these backend services. We've seen that we have an HTTP server that handles auth-related requests from the web app. That server is part of the auth service. We also have some data that's internal to the service itself, a database where we store information about users and organizations. And we have a set of cryptographic secrets. When the server gets a login request from the web app, it checks the database to verify the user's credentials, and then it issues an access token that's signed with our secret key, proving that the access token comes from the auth service. The token that comes back to the web app is a JWT, which contains information about what the user is allowed to access. We can pass this token to any other service, and that service can examine it to perform an authorization check. If the token was issued by our auth service, and it has a valid signature to prove it, and the token isn't yet expired, then we allow the bearer of the token to access any of the organizations listed with the appropriate access level for their role. So for example, when the app wants to display a list of the user's connected Twitch accounts, it makes a request to the Twitch Access service, and it passes along the JWT for the logged-in user. The Twitch Access server verifies that the token is valid, and then it checks to make sure that the organization we're trying to access is one that we actually have permission to fetch data for. If not, then the request is rejected outright. Otherwise, the request proceeds, and the server knows that it's safe to return data for this organization, and only this organization. So the server collects the data for this organization's Twitch accounts and returns that data to the web app in JSON format. This is an example of an API. In this case, the Twitch Access server exposes an API that lets the web app get information about connected Twitch accounts. By sending an HTTP request to this endpoint, the web app is making an API call, allowing it to view and modify data that lives in the backend. But what if we need to affect data across multiple services? For example, we allow a user to delete their organization, which should delete all of the relevant data. The auth service has data about this organization, and it's easy enough for the auth server to remove it from the database in response to that request. But we also have data related to this organization's Twitch accounts in the Twitch Access database. So how do we get rid of that too? We could break encapsulation and have our auth server directly modify the Twitch Access service's database, but that wouldn't be a good idea. One of our core design principles is that a service should own all of its data. If you want to modify the data that belongs to a service, you have to go through that service. So we could instead have the auth server send a request directly to the Twitch Access server, asking it to delete all the data associated with this organization. That's marginally better, but it still couples these two services together. And there are other services too. We really don't want to create a situation where literally every service in our backend is coupled together. The auth server should just have to worry about auth-related concerns. So instead, we use message queues to handle situations where different services need to act in a coordinated way. Once the auth server deletes its data for an organization, it can produce an organization deleted event. This lets all interested parties know that the organization no longer exists, but the auth service doesn't have to care who's listening for this message or what they do in response. As soon as it produces the event, its job is done, and the auth service is no longer in the picture. Within the Twitch Access service, we run a process that simply consumes messages from this queue. Whenever it learns that an organization has been deleted, it purges any data that belonged to it. This approach scales much better. Other services can respond to this event too, and they're all doing so independent of each other. We've seen how the Twitch Access Service serves the web app with data about our connected Twitch accounts. But how does it handle connecting an account in the first place? To answer that question, we need to talk about OAuth. OAuth allows you to grant our platform access to your Twitch account in a way that's secure, that's fully transparent about what kind of permissions you're granting us, and that lets you revoke access at any time. When you click the button in our app to connect your Twitch account, the app makes an API call to initiate an authorization flow. The server responds by recording the fact that you've started this process, and then it sends back a URL that will redirect your browser to Twitch. This way, you're only talking to Twitch. Our app isn't involved at all, so we never see your password, and we aren't given any information about your Twitch account until you explicitly authorize it. Once you confirm to Twitch that you want to grant us access, Twitch generates a one-time code. Then it redirects you back to our app, supplying that authorization code in the process. Our app then makes another API call, passing along the Twitch authorization code to our backend. The server checks the state that it recorded earlier to make sure that everything looks good, and then it sends that one-time code back to Twitch. If Twitch accepts the code, it responds with a user access token, which is what authorizes our app to call the Twitch API on your behalf. The server stores the user access token in its database. Because of this slightly convoluted code exchange process, we can be sure that the access token is a secret that's only known to us and to Twitch. It never goes through your browser. At this point, your Twitch account is now connected to our platform. Twitch accounts are one of the things that we want you to be able to access in scripts. In other words, we'd call it a script-accessible resource. So the last thing we do before we complete this request is produce an event that lets downstream services know that we have a new Twitch account connected in your organization. With that done, we've completed the request to connect your Twitch account. One other thing this service has to do is to periodically validate your user access token. This is something that Twitch requires us to do, so that if you revoke access, we can respond to it in a timely fashion. So we have an additional process that just runs in the background. Every so often, it pulls your access token out of the database and makes a request to Twitch to ensure that it's still valid. So that's everything that the Twitch Access Service is responsible for. As you can see, a service that's designed to address a single problem domain can still have multiple processes to handle different responsibilities. Some of them might do work periodically in the background, others may do work in response to events that are produced elsewhere in the backend, and others do work in response to requests initiated by users. But at this point, we have a user access token for your Twitch account, and we can use it to make requests to the Twitch API. One of the first things we do with it is to subscribe to events from Twitch. We have another service called Twitch Hooks, and it grabs your user access token and calls the Twitch API in order to register some event subscriptions. These are things like your channel going online or offline, viewers following or subscribing, and so on. Whenever one of these events occurs, Twitch will notify us by making a request to our Twitch Hooks server. We can respond by verifying that this webhook request is actually coming from Twitch, then producing an event to another queue. So, if we want to add an entirely new feature to our platform, we can build a new service. Since we're careful not to directly couple our services together except where it's absolutely necessary, our application can offer a complex set of features without it becoming overly complex to maintain. We can freely modify any given service without having to worry too much about how that change will ripple out to other services. And with a basic understanding of backend service design under our belt, we can start to see how something complex like our scripting system could be implemented. Let's say we want to run a user-supplied script like this one. If we're responding to a Twitch follow event, then there's got to be some process that knows how to run our scripts, and it'll need to be sitting downstream from the Twitch events queue so we can respond to webhook callbacks from Twitch. To do things that modify our Twitch account, like setting the stream title, we'll need something in our Twitch Access Service that can get a user access token out of a database and make calls to the Twitch API on your behalf. And the thing that's running your scripts will need to be able to contact it remotely. Since scripts like this are written by users, we'll need something to manage each organization's script files. And when a user is writing scripts, they're calling out to code that's unique to their organization, and that's generated based on the set of resources in their organization. So we need some kind of service that can respond to resource changes and generate these script types. If that's the case, then we might end up with 3 new services to add to our architecture. It's worth remembering, though, that we're making subjective design decisions. Are these 3 different domains or different parts of the same domain? Should we implement them as 3 separate services or one single service? There are pros and cons to either option, and there are good and bad ways to implement either one. As with everything in software development, it's a good idea to have rules of thumb to guide your design decisions, but it's a bad idea to be dogmatic. In this case, I ended up settling on something like this. We have a script type service that generates code based on your organization's resources. Then we have a script file service to manage and compile your script files. And finally, the script runtime service responds to events that occur in the wild by running your compiled scripts. But we still need to figure out how we'll get script-related data into the hands of users who are interacting with our front-end app. We've mostly been focused on the design of our backend so far, but APIs aren't designed in a vacuum. Sometimes an API is an application-agnostic interface to allow third-party access to some system, like the Twitch API, for example. But we're writing internal APIs that are purpose-built for our web app, so we can mold the design of the API to the usage patterns of the app. So before we go any further, we should really take a moment to talk about the design of our front-end application. When you're developing a front-end application, you have to think about two very different concerns: presentation and state management. Presentation is about how you convey information to the user. How do you make the page visually appealing while presenting the relevant information in a readable way? How do you facilitate the user interactions that your app requires? How do you ensure that the user experience is accessible to everyone? State management is more about how you get that information in the first place. Where does the data come from? How do you surface it to the presentation layer so it can be rendered in the UI? How do you store it and keep track of it over time? How do you modify it in response to user interactions? How do you reconcile untrusted client-side state changes with the server authoritative state in the backend? Your approach to state management will depend on a lot of factors. One key distinction is the kind of rendering strategy that your app uses. Some websites are just collections of static pages, so the HTTP server is just serving a bunch of different HTML files for the browser to render. You go to a different URL, the server sends your browser a different file. But most websites nowadays are more dynamic. They might populate the page with different HTML content based on data fetched from some external source, based on your level of access, based on the URL you're asking for, and so on. With server-side rendering, when the browser makes a request for a web page, the server puts the page together on its end and ships a completed HTML document back to the browser. When you navigate to a different page, this process repeats. With client-side rendering, the server sends the entire app to the browser in the form of a big bundle of JavaScript, and that JavaScript bundle knows how to render any particular page. As you navigate around, you're not going back to the server for new pages. Instead, you're triggering state changes and re-renders and asynchronous HTTP requests within the same HTML document. Both approaches have their uses. Our app uses client-side rendering once you're logged in and in the app proper. As you navigate to different sections of the website, the app makes requests to the backend to load the data it needs to display on the current page. On the home page of our app, there's no interactivity. It's essentially just a static page. But when we go to the login page and submit a login request, we start getting data from the backend and storing it locally. This is our application's state. Once we're in the app with an organization selected, that fact becomes part of our app state as well. Now let's say we browse to the section of the app that lets us manage our connected Twitch accounts. The app requests the data that it needs from the Twitch access service and stores it as state. The app can then use this data to render the UI, but this section is the only part of the app that needs data about Twitch accounts. If we browse to a different section of the app, say the collections page, then we forget all about this data and we load some collection-related state instead. If we go deeper and browse to the page for a specific collection, then the app can fetch more data from the Collections API and store it as state for that page. We can think of the structure of our website as a tree. We have some top-level state that's available throughout the app, and then we have different branches for different sections of the app, each with its own set of state. At each point in this tree, the data that we load into state is tied to that branch. It's only available within that section of the website. For these types of resources, then, our state is pretty simple to manage. It just so happens that the structure of our website dovetails nicely with the design of our backend here. Each section of the app manages a specific type of resource. Each type of resource is owned by a single service, so each service can expose an API that the relevant section of the app can use as a client. This design gives us basic CRUD operations for the different resource types in the app, and the front-end implementation is pretty straightforward to maintain. But our scripting system is different. The app needs to keep track of a lot of different data, and we surface fetch state at many different points throughout the app. In the script editor, we render a full-featured text editor that contains all of an organization's script files. These files are fetched from the backend, and the app keeps track of edits that the user makes locally. We also display real-time compilation results in the editor, and the list of editable files is shown in the main navbar. The UIs for the different resource types can access script state as well. For example, when we look at the admin page for a particular command, the app knows whether there's an existing handler function for that command in our script files. There's also the event types page where we list the set of event types available to our organization. These are dynamic, so they're fetched from the backend as well. And there's the event log, where we display all the events that have occurred recently. What's more, we want the app to update in real time. If a new event type gets registered, or if a new event occurs, we want to see that change reflected immediately without having to refresh the page. This means that the app doesn't just need to fetch all this data from the backend, it also needs to keep a connection open so that the backend can push out update notifications in real time. So in short, we're not just dealing with simple CRUD operations on a resource type that lines up one-to-one with the structure of our front end. Our scripting system is fairly complex, and we've landed on a design where the script-related data that our front end needs is owned by multiple services. We could expose an API for each of these services, but we don't really want the web app to have to deal with all this complexity. Instead, we can establish a separate API that's purpose-built for the web app. It gives the app everything it needs to facilitate the script authoring experience. Behind the scenes, this API can aggregate data from our original services, but from the front end's perspective, it doesn't really matter how that happens. All the front end has to do is establish a new script authoring session, and it'll get back all the relevant script-related data for this organization. It'll also get a token that it can use to request real-time updates from the server. This HTTP connection stays open, and whenever the script authoring server gets word of a relevant change to this organization's script data, it'll send a notification to the client, which can then update its state accordingly. This is a pattern known as server-sent events, or SSE. So, in our backend, the script authoring API has taken on the responsibility of communicating data to the web app. That means our original 3 services don't have to expose browser-facing APIs. They just have to communicate with the script authoring service. That communication takes place entirely within the backend, so we're free to use any method of communication we want, like, for example, gRPC. gRPC is a framework for making remote procedure calls, so that code running in one process can cause something to happen in a different process. In a lot of ways, it's very similar to an ordinary HTTP request. One endpoint acts as a client, with the other acting as a server. When the client wants to invoke an RPC on the server, it sends a request over HTTP, passing along a request message. Once the server has done whatever work it needs to do, it can send back a response message. But with gRPC, before you write any application code in either the server or the client, you start by formally defining the interface between them. This schema, written in protocol buffers, describes the operations that the server supports, along with any data structures used in those operations. We can feed this file into the protobuf compiler in order to generate most of the application code we need. When we implement the server, we just have to provide an implementation for each of our gRPC methods. There's no other boilerplate to write. And our client implementation is essentially free. We can just generate all the code necessary to invoke these methods in any programming language, and then all we have to do is use that generated client. This way, we have a schema that serves as the single source of truth for how our server works. All the relevant application code is guaranteed to stay in sync with those definitions, so these points of direct contact between different parts of our backend become much easier to maintain. Okay, we've gotten acquainted with the fundamental concepts at play in our web app. We've looked at the backend to see how data is stored, how API requests are authorized, and how resources like Twitch accounts are managed. We've looked at the front end to take stock of the user-facing functionality we want to provide, and to understand how we want data to flow from the server to the client. And we've sketched out a design for our scripting system that involves multiple different services. Now let's figure out the details of how we're going to implement those services. We've looked at some of the key factors that guide the design of any web app, So for the rest of this video, we'll dig into some of the novel problems that we have to solve for Bigtime in particular. Our platform lets the user write code in TypeScript, and then we run that code as JavaScript. So we need to learn a few things about JavaScript and TypeScript, and we need to think about what it means to run code that users have written. JavaScript is everywhere. It's in the browser where it lets us run all our client-side code, but it's also a popular language for backend development. We've chosen to write our backend in Go, but plenty of people use JavaScript as a server-side language using a runtime like Dino or Node.js. We want to take our users' scripts and run them server-side. So a naive approach might be to take that user-supplied code and run Node to evaluate it. But this would be a very bad idea. The user could do all sorts of unseemly things to the servers we're running their code on, and restricting the power that Node gives them would be an impossible game of whack-a-mole. Really, Node just isn't the right tool for the job. We don't need a powerful runtime for writing applications, we just want a simple script interpreter. This is one case where it's important to try and speak precisely about the different pieces of a JavaScript ecosystem. So let's try and make some distinctions. JavaScript as a language is described by the ECMAScript standard. This is a 700-page document that outlines exactly how the language works: variables, control structures, functions, and so on. The core of the language, sometimes referred to by a standard version like ES6 or ES 2020, includes basic things like objects, arrays, and strings. Web browsers build additional functionality on top of JavaScript. These are more loosely standardized features that have evolved along with the web over the past 20 years or so. Things like Windows and Documents and the Fetch API are specific to browsers. They're not part of the ECMAScript standard. Node lacks a lot of that browser-specific functionality, but it adds in a lot of features that you need for server-side application development. Under the hood, Node and Chrome both use V8, which is Google's JavaScript engine. V8 is the thing that actually implements the ECMAScript standard. Let's say I open the console in Chrome and I enter this bit of JavaScript, which should give me the URL of the current page. Chrome takes my JavaScript code and passes it into V8. V8 knows how to evaluate JavaScript. It looks for a variable named window and resolves it to an object, then it accesses a property on that object called location, and so on. Eventually, it evaluates this expression to a string value and returns it to Chrome, where Chrome can display it to us. If I open up Node and I run the exact same expression, Node passes it into V8 just the same, and V8 evaluates it according to the exact same rules. The only difference is that Node doesn't define a global variable named window, so we get an error instead. But of course, there are other globals defined in Node that don't exist in the browser. So for evaluating user scripts in our platform, we don't need or want any of this extra functionality. We can just write our own application that runs our user's code directly in V8. But just like Chrome or just like Node, our application needs to provide the extra bits of functionality that we want our users to be able to access from JavaScript. So we'll have to figure out how to do that. But first, you may be wondering, we actually want users to write their code in TypeScript. So what's the difference there? JavaScript and TypeScript are separate beasts. They're both programming languages, and one is a superset of the other. But the rubber meets the road for them in very different places. JavaScript is a language that you can write code in. You can then run that code in a JavaScript interpreter like V8. TypeScript is also a language that you can write code in. You can then compile that code to JavaScript in order to run it in V8. Let's look at our example script again. If we were just writing it in plain JavaScript, it would look pretty much the same as if we wrote it in TypeScript. The difference is that there are a bunch of questions about this code that we can't answer without running it. Is handlers.onTwitchFollow something that we can actually define this way? What is O? What is E? How do we know that evaluating e.viewer.displayName will give us a valid string? How do we know that e.account.setStreamTitle is a function that takes a string? In the good old-fashioned world of pure JavaScript, there's only one way to answer these questions. We run the code and see if we get an error. With TypeScript, we can know the answers to these questions at compile time instead of at runtime. We just need to supply some extra type information. That is, we don't have to guess about how all these variables and properties and functions work. We can explicitly declare all those details. All of these declarations are provided by our platform. And then this part is what the user writes. We can take both of these things and feed them into the TypeScript compiler to check that our user-supplied code is correct. This type checking process goes like this. Is handlers defined? Yep. Does it have a property called onTwitchFollow that we can assign to? Yeah. Is this value a function that takes these two parameters, something we can assign to that property? Yeah. So, okay, this expression isn't going to cause an error when we run it later. Next, is E going to be a valid object? Yeah, looks like it. And will that object have a property called viewer? Yep, that's an object of type TwitchViewer. Does a TwitchViewer have a displayName property? Yep, so we know that this expression will be a string. And we know that adding a string to a string gives us another string, so we know that title is going to be a valid string. We can do the same thing for this last line. We can figure out that e.account.setStreamTitle will evaluate to a function that takes a string, and we know that we're calling it with a string, so our whole program is well formed. This is what the TypeScript compiler does. It type checks our code to make sure it all makes sense according to the type definitions we've given it. Once it's done type checking, it can simply strip the extra type annotations out of the statements that actually do something, and it can throw out all the type declarations that are just there to help the compiler. And what we've ended up with is JavaScript. We're back where we started, but we now have the added guarantee that our code isn't going to produce any of these kinds of errors when we run it. And this compiled JavaScript is what ultimately gets run in V8. If we just run this code by itself, we'll get an error since handlers isn't actually defined. But if we do a little bit of setup to prepare our script evaluation context first, and then run our user-supplied code, then we can do something like this when it's time to respond to a follow event from Twitch. When V8 gets here, it'll jump into code that the user wrote. And from there, it can jump back into our code to use functionality that we've provided. So how do we provide those type definitions? And just as importantly, how do we provide implementations for functions like setStreamTitle? Let's talk about how all this code gets generated. Every organization has a different set of resources. Your scripts will have access to your Twitch account, my scripts will have access to mine. And in fact, there are many different types of resources besides Twitch accounts. Each one is described by a resource schema that gets published whenever the underlying resource changes. In addition to these resource types, we define a set of script modules. Each module defines the rules for how code should be generated based on a set of input resources. For example, our rules for generating code based on Twitch accounts look something like this. We define two files that we want to generate, and each of those files depends on the full set of Twitch accounts that are connected in our organization. For each file, we define a function that takes in those Twitch accounts and spits out the contents of a TypeScript file. The .d.ts file contains type declarations. This is what we use for type checking when we run the TypeScript compiler. And we also expose this file to the web app so that the user gets IntelliSense hints and type checking in the code editor. This other file is private. The user never sees it. It contains the TypeScript code that actually implements those type definitions. So let's take a closer look at these two generated source files, starting with the type declarations. When we're generating code, we can output any valid TypeScript source. For example, we can describe the basic data types that should be defined as long as we have at least one Twitch account connected. That also includes the types of events that can be generated from connected Twitch accounts. Here we define an interface that describes the data we can access and the operations we can perform on any connected Twitch account. Here we augment the global handlers interface to specify which event types are defined by this module. And finally, we can augment the global organization interface to provide references to our connected Twitch accounts. This file is the contract that tells the user precisely what they can do in their scripts. It's still up to us to actually fulfill that contract, and we need to start by generating a corresponding implementation file. In this file, we define a class that implements our Twitch account interface. And then for each connected Twitch account, we prepare a subclass that's initialized with all the relevant data. Finally, we establish the global data on these handlers and _o objects that we assume to already exist to match our earlier declarations. You'll notice, though, that we access this other global variable called _l, which seems to have a property of type pb.twitch.lib. And our setStreamTitle function just seems to be a stub that calls another function on that object. This function is provided by our script runtime. When we call it, we jump out of V8 and into native code. And ultimately, we end up calling a gRPC client function that makes a request to the Twitch access service. So let's look at how we use gRPC in the script runtime. Here's another look at our architecture. Earlier we saw how the Twitch Access Service manages your connected Twitch accounts. Let's simplify our view and consider what happens during script execution. We have our Twitch Access Service, and elsewhere in the platform within the script runtime service, we have a process that's running our user scripts. This is the thing that runs all of our compiled JavaScript code in V8. The Twitch Access Service contains a Twitch user access token for our connected account. And in order for our script to do things like changing the stream title, we need to call the Twitch API with that token. So one thing we could do is provide that token to the process that's running our scripts, and then it could make a Twitch API call directly. But that breaks encapsulation, and it's also a security concern. The user access token is a sensitive piece of data, and it's better if we keep it well away from the place where user-controlled scripts are run. Instead, we'll leave Twitch API calls to the service that handles Twitch API access. We can once again use gRPC and create a schema that establishes all the Twitch-related functionality that scripts might need to use at runtime. Within the Twitch Access Service, we'll create a gRPC server, and we'll implement the setStreamTitle RPC by getting the user's access token from the database and using it to make a Twitch API call. Then our script runtime's worker process can just use the generated gRPC client whenever it needs to change the stream title. This is a common pattern within our platform. Any service that needs to expose library functionality to scripts can run its own gRPC server, which we call the lib server. And our script worker uses a corresponding gRPC client to invoke that functionality. We still need to consider authorization. Our gRPC server needs to verify that the request is coming from our own internal script worker process, and it needs to determine which organization the script is authorized to access. So before we execute a script, we contact the auth server to request a JWT. Since we're not identifying a user based on credentials, our authentication process is slightly different than logging a user into the web app. The script runtime service requests a short-lived token that will authorize script execution within a specific organization, and it signs that request using a secret key that's known only to it and the auth service. So when we supply that token to our gRPC server, it can verify the token and see that it authorizes us to access the Twitch accounts for our specific organization. But there's one more piece to this puzzle. We need to make it possible for user-authored scripts to initiate these gRPC calls from JavaScript. And that's going to require one more layer of code generation. Let's dig into this process that runs our scripts to see more. As we just saw, we have a script library interface for each service, which defines all the functionality we can invoke from scripts. Since we're using gRPC, we can generate a client that lets us invoke these operations remotely from our Go program. Within our script runtime's worker process, we have this gRPC client, and we can call setStreamTitle on it when we want to change the stream title for any connected Twitch account. Of course, we're not making hard-coded calls from a Go application. We're invoking these functions from JavaScript code that's running in V8. So we need to wrap our generated Go client in something that's callable from JavaScript. As it turns out, it's pretty straightforward to write custom plugins for the protobuf compiler. So we have our own plugin that takes in this gRPC schema and spits out a different set of Go code that we then use to wrap our gRPC client. This function is compiled to native code, and it serves as the glue between JavaScript code running in V8 and the rest of our application. It reads in two function arguments and then calls our gRPC client's setStreamTitle function. We also generate this bit of code, which we can use to create a JavaScript object with bindings for all our gRPC functions. Our JavaScript code can call this function, and it'll end up running our native wrapper function as a result. But this is just a plain JavaScript object that we create at runtime. Since we're using TypeScript, we also need to generate type declarations for our library object. This file isn't used at runtime, but it's made available when we compile TypeScript, so the compiler knows which functions actually exist for us to call. With all of this generated code, we have an object defined within our V8 context that exposes our gRPC interface. When we respond to an event, we initialize our V8 context with the set of wrapper objects representing each of our script libraries. Then we initialize the object that represents your organization and its resources by running all the internal JavaScripts that we generated from those resources. Then we bring all of your organization's user-provided code into scope. And we initialize the object that represents the payload for whatever event we're handling. Finally, we kick off script execution by calling the appropriate event handler function. At this point, we're running your code. Your code can then jump into code from those internal implementation files, and our internal script implementation can call lib functions that we've generated from our gRPC schema. Those functions then call the appropriate gRPC client function that was compiled from Go, and we complete a request to the appropriate lib server. The user is just presented with a simple set of functions they can call, and under the hood we take care of all the details in a way that's scalable and secure. All this client code is generated, so it's pretty easy to add new script-accessible functionality. We just have to update the gRPC schema, and then once we've implemented the new operations on the server, we can just regenerate our client code, and we'll have access to our new functions. Now we can finally wrap up our look at the scripting system. This is an overview of how data flows through our scripting system at different points in time. First, for each service that exposes script library functionality, we define a gRPC schema. Then we compile that schema to generate the Go code for our client and server, a V8 wrapper, and the accompanying TypeScript declarations. This is a process that happens offline whenever we add or update script support for one of our services. Next, we come to where users interact with the app to create and manage script-accessible resources. For example, the user can connect their Twitch account. That results in a resource schema change. Our script type service picks up on this change and generates the TypeScript code that depends on that resource. In this case, that's a private implementation file and the accompanying type declarations, representing all the Twitch-related code that user scripts can access in this organization. Once we generate a TypeScript implementation, we need to compile it to JavaScript. This type checks it to ensure that the contract we're establishing with the user in our declaration file is actually fulfilled by our implementation. Since our implementation uses our gRPC interfaces to do the heavy lifting, we pull in those types as well. That compile gives us a JavaScript file that we can run to establish all our Twitch-related functionality at runtime. It also gives us a source map file that links the statements in our compiled JavaScript file back to the corresponding statements in the original TypeScript file, which is helpful when we're looking at stack traces from errors. As part of our TypeScript compilation process, we also perform some analysis on the generated code. In particular, we parse the set of event types that are defined in our type declarations. This information is fed into the Webapp, so the user can be presented with a list of valid events they can define script callbacks for. The code editor allows the user to write their own files, and it has access to all the relevant TypeScript declarations, so it can provide hints and run accurate type checks client-side. Whenever the user saves their changes to a script file, we take all their scripts and run them through the TypeScript compiler. We use the same set of type declarations to type check the code, and if the compile succeeds, we end up with another set of JavaScript files that are ready to be executed at runtime. In this compile step, we do some extra analysis as well. This time we parse the user-supplied script files to determine which event types have callback functions bound to them. So later on, when Twitch notifies us that someone has followed this user's Twitch account, we know that there's script code that the user wants to run in response. After all this setup, this is where we actually start executing the user's scripts. In our script runtime process, we have gRPC clients that let us make requests to other services. We also have a V8 context that allows us to run all of the JavaScript needed to handle the event. Within that V8 context, we initialize JavaScript bindings for all of our gRPC clients. Then we initialize that context with all the code for the relevant organization. That involves executing all our generated implementation files, then executing compiled versions of our user-supplied scripts. Finally, we can set up an event payload and invoke the appropriate event handler function. Of course, if something goes wrong, we want to present the user with accurate error information. So we also need to pull in the original TypeScript source files and the source maps for all the relevant code. Once our user-supplied event handler function is finished running, we've finished responding to the event, and we can log all the relevant results for the user to see. So this script system involves 4 different stages, essentially. There's the gRPC code generation that happens offline as a result of us adding script support to one service or another. Then there's the TypeScript code generation that happens in response to users adding or modifying resources within the platform. Then we allow users to author their own scripts, which we compile and prepare for execution. And then finally, we have the process that gets kicked off when events occur, which actually invokes the user's function and runs all of this code. We've looked at Twitch as an example, but this same system supports all of our script-accessible functionality. Swap out this part, and you've got a different set of library functionality that's owned by a different service. Swap out this part, and you've got different types of resources that can be accessed from user scripts in different ways. And swap out this part, and you've got a different mechanism for triggering script execution in response to a different set of events. Regardless of how many different services we extend with script support, the guts of the scripting system are the same, and the user experience is the same. From a user's perspective, all of this complexity is hidden. They just create the resources they want to use, and when they go to write scripts, all the relevant type information is right there in the editor for them. Once they've saved their script and the relevant event occurs, then their script gets run and it does whatever they've told it to do. Simple as that. By now, we've walked through concrete examples of all the different building blocks that make up our architecture. So let's try and summarize the overall design of our app, and hopefully it'll make some sense. Broadly speaking, our architecture is service-based. It's modularized or split into smaller chunks, with each service taking responsibility for a specific domain or problem area. In our application, there are two key factors that define a service. One is that a service owns the data that's relevant to its problem domain. So for us, databases are internal to a particular service, not shared between them. The other defining factor is that services are deployed independently, and as such, they should be minimally coupled. If one service needs to respond to changes that originate from another service, then it's preferable if that can happen asynchronously using queues. We also allow a service to contain any number of processes. We don't cram multiple different workloads into a single process. A process might just consume events from a queue, or it might run some periodic background task, but it can also expose APIs to permit the outside world to access and modify the service's data. If it's interfacing with other services in the backend, then we tend to use gRPC. And if it needs to serve data to a front-end app, then we'll use HTTP. Any of these processes can write to a database, read from a database, produce to queues, and consume from queues, whatever the design dictates. The primary client of these services is our Webapp. It uses client-side rendering to present the user with a richly interactive UI, and so it fetches data from the backend as needed via HTTP. These are the basic building blocks that we use to design each service. If we zoom out a bit, we can look at the actual services that make up the Bigtime platform and how they fit together. The Auth service handles authentication and authorization, and it establishes the core concepts that the rest of our platform is built around, like the concept of organizations. It exposes the APIs that allow users to log into the app and manage their organizations. The Auth service produces events to a queue when a user account or an organization is deleted, so that those changes can ripple out to other services. Next, we have a series of services that each implement a particular feature. They each own some set of resources, and they expose APIs to let the user manage those resources. Some of these resources are designed to be accessible from scripts, so we define a resource schema for each of those types. Whenever a service changes one of these resources in a way that affects how it's represented in scripts, the service produces a schema change event to another queue. Some of these services are also capable of instigating script events, which is handled by producing to yet another queue. For example, when a command is manually invoked, the command service produces a script event. Our Twitch integration has a few extra moving parts. We have a service that handles webhook callbacks from Twitch by producing to another queue. Then we have yet another service that translates those Twitch events into script events. Finally, we have the scripting system itself, which is implemented in 3 different backend services. In addition, the script authoring service serves as the interface between the backend and the web app. Whenever any service changes a script accessible resource, it produces an event containing an up-to-date description of that resource. The script type service responds to these events. It has a set of script modules that it uses to generate TypeScript code to wrap an organization's resources. Anytime the script type service generates new files, it kicks them downstream using another queue. The script authoring service consumes these events so it can provide real-time updates to the web app whenever public type declarations change. These generated files are also stored by the script files service. The script authoring service can fetch the full set of files using gRPC. And it also makes a gRPC request whenever the user saves their changes in the script editor. When that happens, the script file service kicks off a process that attempts to compile the organization's scripts. The service uses another queue to propagate file changes and compilation results, both to the web app and to the next stage in our pipeline. Finally, then, we have the script runtime service, which collects the full set of TypeScript and JavaScript files ready to run the latest version of an organization's scripts whenever an event occurs. When an upstream service instigates a script event, it produces an event to this queue. The script runtime service responds to that event by deciding whether script execution should take place. If so, it uses another queue to kick off that process. Changes in execution status are produced as events to the same queue. All of these events are propagated to the web app via the script authoring service in real time, and the script authoring service can fetch a full set of historical event data using gRPC. Most of these queues are used as event queues. A message in one of these queues records that some event has happened somewhere in the platform, and that message is fanned out to any number of different consumers. These queues, by contrast, are work queues. A message in one of these queues represents a pending task that needs to be performed, like a script compile or script execution, so the message is distributed in round-robin fashion to the first available consumer. These worker processes are designed to be isolated from the rest of the platform. Since they have a relatively expensive performance cost and highly variable frequency, we're able to scale the number of workers up or down pretty easily. We also want the compilation and execution processes to be isolated so that users can't affect the overall stability of the system by monkeying with their scripts. The script runtime is designed with security in mind. As we saw earlier, we never make sensitive information like access tokens accessible to scripts running in V8, and the entire process is designed so that it doesn't need to access the database at all. Everything it needs to run is contained in the original event, and when it's ready to record execution results, the process simply produces to a queue that another process can read from in order to update platform state. Beyond that, the worker just makes gRPC calls to other services whenever it needs to do anything that affects the state of our backend. It can do this, of course, because those services implement the gRPC schemas that form our script library, and we use the same set of gRPC schemas when building the worker process. This is a more or less complete picture of Bigtime's architecture from a high-level view. When you're designing a system like this, a great way to evaluate it is to ask yourself, what would it take to implement a new feature? For example, let's say we wanted to support YouTube live streams in addition to Twitch. How would we fit that feature into our architecture? We'd want to create a service, and we'd probably start by modeling the data that this new service would own. We'd also want to ensure that we delete any user data in this service whenever the relevant organization or user is deleted from the platform. Next, we could establish the APIs that would expose our data to the app, and of course we'd need to build the relevant UI in our front end. After that, we could add scripting support. We'd want to define a resource type for connected YouTube accounts, and we'd have our service produce events whenever a resource change occurred. We'd also need to write a gRPC schema establishing what script-accessible functionality we want to provide for YouTube accounts, and we'd implement a lib server in our new service. Then we'd add a script module to the script type service and write the templates that would be used to generate the TypeScript code that would make YouTube accounts accessible in scripts. From there, we just need to update our script runtime service to use the latest gRPC client so that it can make requests of a new service. With that, our new feature would be ready to use. I hope this has given you a decent understanding of how Bigtime works under the hood. We've covered a lot of ground to get here, and I hope you've learned something from our exploration of all the background information as well. I am quite proud of this project, and after all the work I've put into it, I wanted to show it off. But I also saw it as an opportunity to distill what I've learned about web development over the past few years and share that understanding with a wider audience. Coming from a game dev background, I've found that a lot of educational content in the world of web development is weirdly fixated on frameworks. And there's a lot of simple tutorial projects, but comparatively little that deals with the fundamentals of software design applied to real-world production-scale projects. If you're just writing another to-do list app, then a lot of the trade-offs inherent in these sorts of architectural choices are hard to see. But once you're considering them in a real project at scale, I think they become pretty self-evident. So hopefully you've learned something, no matter what your background is, and thank you for sticking with me. I'd also like to give a very special shout out to Motion Canvas, which I use to make all the graphics in this video. It's an incredible tool, and I couldn't have made this video what it is without it. If Bigtime Stream Tools looks interesting to you, either as a product you'd like to use, or as an investment opportunity for the millions of dollars you have lying around, you can find out more at bigtime.stream. And if you have questions about anything we covered in this video, please feel free to bring them up in the comments. I welcome the chance to have a civil discussion. Until we meet again, thanks for watching.